Can we achieve faster-than-light travel? That's the big question, isn't it? It is important, though. Throughout the history of sci-fi, it's been explored many times, but usually never backed up as to how it could happen. That was usually glanced over. And faster-than-light travel is something we want. Warping at many times the speed of light to explore our entire universe is an alluring idea, especially if we want to someday meet intelligent alien life. It's infectious even. So how do we do that, speaking in terms of the real universe? Unfortunately, there have never been very many ways to do it according to known physics. In fact, it's almost hostile to the idea. Breaking the speed of light within Einstein's relativity, the best description of the universe at large that we have, would require infinite energy. Infinite energy isn't possible. Or is there another way? Is there a way to essentially hack the universe and move its speed so fast that science fiction generally didn't imagine until science itself actually did? My guest today explored just such a concept after watching an episode of Star Trek and thinking about how a warp field could be established that would allow faster-than-light travel. It's just an idea consistent with relativity. There's no guarantee it would actually work, but it's one that so far has stood the test of time. People still wonder about this idea over 20 years after its formulation. As I said, it's consistent with relativity, but with caveats, pretty big ones. But it's important to explore the idea nonetheless. After all, if we respond to all ideas as inherently impossible, we'd have never gotten very far as a civilization. So, can we actually travel faster than light?
Welcome to Event Horizon with John Michael Godier. Joining John in this episode is theoretical physicist Dr. Miguel Alcubierre. Dr. Alcubierre received his PhD in 1994 through the study of numerical general relativity and has since worked at the Max Planck Institute for Gravitational Physics in Potsdam, Germany, and the National Autonomous University of Mexico. Dr. Alcubierre is best known for his 1994 paper, The Warp Drive: Hyperfast Travel Within General Relativity, where he describes his theory for traveling faster than light with what's become known as the Alcubierre Warp Drive.
Welcome everyone to Event Horizon with me, John Michael Godier. If you enjoy what you hear, fall into the Event Horizon, hit the like button, and become an active subscriber by ringing the bell. Miguel Alcubierre, welcome to the program.
Hi, hello.
Doctor, everybody knows you for your warp bubble concept, but you've done a lot of science. That was 1994. You've done a lot of science since then. What does your work focus on these days?
Well, on these days, I've been working on black hole formation and also on something a little bit esoteric that we call boson stars, which is a model for a star made of a special kind of field that could mimic a black hole in many circumstances. So I've been specializing in that area, and my work is mostly numerical simulations. So for a long time, I've been doing numerical simulations of black hole spacetimes, formation of black holes, collapse of stars, and also gravitational waves, production of gravitational waves. So that's my main work, and I've been working on that for the last 20-odd years.
We recently detected with the LIGO experiment the formation of, or the coalescing of two neutron stars. And I suppose that would be even more applicable to black holes if you have a binary black hole that's merging. Now, do you study that?
I've studied binary black hole formation, collision of binary black holes, not so much neutron stars. Neutron stars are difficult for different reasons because they have a lot of matter and you have to do fluid dynamics and maybe magnetic fields and things like that. Black holes are cleaner. And I've been studying black holes for a long time. So during the 90s and even early part of the 2000s, my main work was black hole simulations of black holes that collide in an inspiral. They're orbiting and then they do an inspiral collision. And that was actually the first thing detected by LIGO. 3 years ago, they detected the first gravitational wave detection ever was a collision of two black holes, which is exactly the problem I have been working for a long time.
Now, when black holes merge, collide like that. How long does that process take before they become entangled and gravitationally and they actually collide?
Depends very much on how they formed, but it could take tens of millions of years. It's a very, very long process. It's very slow. They approach each other very slowly because they're emitting very low gravitational waves, energy. They're losing energy in gravitational waves, but it's very, very slow. And those gravitational waves, in principle, cannot be detected because they're extremely weak. But this process takes millions and millions of years. But eventually they get to the point in which they're very, very close, and they're separated just by a few times their own radius. And at that point, the whole process can take just fractions of a second. And that's what we detect. So the detection of gravitational waves from a black hole collision typically only detects the less than a second, the last fraction of a second of a collision. That's what we can detect. And the first detection, actually, the whole thing lasted for about 20 parts of a second, so 1/20th of a second or something like that. It was really very, very close. Neutron stars actually take longer. So when two neutron stars collide, we can detect the last minute or so of the collision. And that's because they're usually closer by, so the signal is stronger, and it's also more in the range of the detector, so we can detect for longer. But black holes is a very, very fast process what we can detect.
So when you have two incredibly dense objects, like two black holes or two neutron stars for that matter, this has to be a ridiculously abnormal environment. Do you see things like, so you create gravitational waves, but what other radiation comes out of that? Do you see like this perhaps a solution to something like fast radio bursts, where you just see this mysterious burst of radiation that comes out of nowhere? Could that be from these kinds of mergers?
That's exactly what we think. Not from black holes. When two black holes merge, then nothing else happens. It's only gravitational waves, because black holes are vacuum. They have no matter. The matter has all been concentrated in the center, and the center is beyond the horizon, so it cannot, nothing that happens inside the black hole can affect us, and no radiation comes out from there. So when two black holes collide, all you get is gravitational waves. But when two neutron stars collide, that's very different, because neutrons are made of matter, they're made of fluids, and they have magnetic fields and etc. So when two neutron stars collide, essentially you get fireworks. You get a huge explosion, and this explosion produces radiation in all wavelengths. And in principle, yes, we believe that part of the gamma ray bursts that have been detected for the last 20 or 30 years by satellites come from collisions of neutron stars. There are actually two different types of gamma ray bursts, what we call the long-lived and the short-lived. And we believe that the short-lived are mainly caused by collisions of neutron stars. The long-lived, we're still not sure, but the short-lived are probably almost always the collision of two neutron stars. And this is extremely interesting, because if we can get the information from the collision of the neutron stars with gravitational waves, and also we can detect them also with gamma rays and other things, then we can learn a lot about the system. We can even do cosmology. So these types of systems are far more interesting. At the moment, there's only one confirmed detection of a collision of two neutron stars from LIGO, from gravitational waves. That was just over a year and a half ago. And there hasn't been another announced, but maybe they've seen something in the last few weeks and they're a bit cautious about announcing it. There might be some hints about it. But those are the extremely interesting systems. Collisions of stars give us a lot more information about the universe.
Now, is that due to the fact that nothing can escape a black hole's event horizon? So if you have two black holes coalescing and falling into each other and becoming a single black hole, you can't get anything except gravitational waves because nothing can escape the black holes. So you can't get any kind of radiation other than, I guess, maybe some kind of Hawking radiation off it. So is that the case, that they're just simply...
That's exactly the case. When two black holes collide, there's nothing else there. It's just the two black holes. There's nothing can escape from inside the black holes, so there's no light, there's no radiation of any kind. The only thing you get are gravitational waves. So in that sense, it's a very clean system, but it's also, you can only detect it on gravitational waves and nothing else. Even the Hawking radiation is a concept that is theoretically very well understood, but we've never seen evidence of that, because for a black hole the size of a star or bigger, which is the ones we've seen, the Hawking radiation is completely negligible. It can just be ignored completely. There's no hope of detecting it. So what you detect is just the gravitational waves coming from the collision. Still, that's very interesting. That was the first system we saw, and we've seen about 10 maybe a lot more now because LIGO's already taking data again. But until the beginning of this year, we've seen about 10 collisions of black holes with LIGO. When I say seen, I actually mean observed with gravitational waves, not with light. But so that happens sufficiently often that we see them a lot. Collisions of neutron stars are not that easy to see because if they happen very far away, you can't see them because the signal is very weak. They have to happen very close by, so you might be able to detect them. But black holes you can detect very far away because they're usually bigger, and that means that the signal in gravitational waves is much stronger. But that's all you get. So you get the gravitational wave, you know it was two black holes. You can measure the distance because of the gravitational waves, and you can get the mass of the black holes, and maybe, if we're lucky, even how fast they were rotating. But it's very difficult to know exactly where they were. So we cannot pinpoint the galaxy in which the black holes collided because there's no light coming out of the system, and the gravitational wave doesn't allow you to locate this in space very well. So you can sort of say it came from that region in space, but we don't know exactly where. Whereas with neutron stars, it's much more different because if you see the light, then you can pinpoint the galaxy exactly.
What would the Hawking radiation of a black hole look like? Would it be gamma rays?
Well, yeah. Hawking radiation is, as I mentioned, is a theoretical idea that came from Hawking in the 70s. It still has not been confirmed observationally or experimentally. But basically, Hawking radiation is just what we call black body radiation. Now, a black body is not the same as a black hole. A black body is just physicist terms of saying something hot. So we call it a black body because it absorbs everything that falls into it, and then emits the light back as just heat. So the sun, even though it's not black, it's yellow. But it's a very good approximation to a black body in physics terms. It's just something that emits light because of its hot. It is hot. And depending on how hot it is, it emits light in different wavelengths. So if it's not very hot, you can't see it. If it's a little bit hotter, you see it red, and hotter still than yellow. And if it's very hot, you see it blue. Now, black holes emit radiation just like this, black body radiation. But the temperature of a black hole is inverse to its mass. That means that very large black holes are essentially very cold and emit very little radiation, and radiation you cannot see with normal light. It would come in radio waves. So for a black hole the mass of a star, the Hawking radiation would come in the very, very far radio waves and would be so weak that we wouldn't be able to detect it at all. If the black hole was very small, and when I mean very small, about the size of an atom or something like that, I mean really small, with the mass of a few atoms, then it would emit radiation very, very hot, and it would come out in gamma rays, probably. But we haven't seen that. It's very difficult to detect. So there's no proof yet, observational proof, that Hawking radiation exists. It's just a theoretical idea.
Now, to get into the concept of a star drive that you could use a black hole to drive, the smaller the black hole, the more radiation it emits, right?
Yes, that's correct.
So if you saw, I mean, could there be like a technosignature there, as they say within astrobiology, a technosignature? Would an artificial, very small black hole, low mass, would that be visible as something that you could say that is an alien star drive driven by a micro black hole?
Not really, because the process would be it's very fast. So a very small black hole would emit Hawking radiation so fast that it would evaporate very quickly. And what you would see essentially is probably something more like an explosion, a burst of gamma rays. So some people have actually speculated that gamma ray bursts are actually black holes evaporating, but the idea doesn't fit very well. But you would see some sort of burst of radiation, and that's it. It would die very quickly. Because the black hole, as it emits radiation, it loses mass. And the smaller it is, the faster this goes. So a very small black hole would evaporate very quickly in a matter of seconds. So you wouldn't see something that just emitting Hawking radiation for a long time. You would see a burst of radiation and then it's dead, right? It would be something very quick. And also it depends on the size. If you have a small black hole that's still a few grams in weight, that would still not emit enough Hawking radiation for us to detect it. It would have to be something that weighs not much more than a few atoms, and then you would see a lot of radiation, and it would happen very quickly.
So you would see it as burst, but so say you had a Kugelblitz, essentially, a tiny little black hole that you've artificially created with lasers. It would radiate in a certain way, but very rapidly, if I'm understanding you correctly. So you would see it evaporate almost instantly.
Exactly, yeah.
Now, you're also known for the Alcubierre Warpfield, and I call it the Warpfield because, you know, a lot of people say star drive, but it's really the idea of warping space-time. At its most basic, what is the Alcubierre warp field?
Well, the idea is just a way in which you can deform space that would allow you to travel, in principle, as fast as you want in space without actually moving. So it's as you mentioned it correctly. It's not a star drive. It's not a machine. It has nothing to do with a spaceship. It's just a model of what you would need to do to space to be able to move very fast. And the idea is to use the fact that space can be deformed. And according to the theory of relativity, Einstein's general relativity, gravity is just a deformation of space. It's a deformation of the geometry of space. So space can be curved. Usually people here talk about the curvature of space or space-time. But curvature is a very generic name. So you can do many things to space. You can expand it and you can contract it, for example. And we've all heard about the expansion of the universe. And that happens because space is expanding. So people usually don't understand that correctly, because they think that if space, the expansion of the universe, they think it's because galaxies are flying apart because there was some huge explosion somewhere. But it's not like that at all. I mean, galaxies are not flying apart. Galaxies are just sitting there quietly in their own corner of the universe, but space between them is expanding. It's being stretched. So you can do that to space. You can stretch space, and you can also contract space. And then the idea I had back in '94 was that you can do this in a very small scale. So if you imagine that you do a very violent but very localized expansion of space behind you, that would push you away from things that are behind you. And if at the same time you do an opposite contraction of space in front of you, that would pull you towards things in front of you. And the net effect of those two things combined is that you would move. You would move through space. You would get away from the things behind you and closer to the things in front of you. But you would not be moving yourself. You would be sitting in a bubble of quiet space, if you want, with a violent expansion behind you and a violent contraction in front of you. And that would, apparently, you would move through space without moving at all. So it was space doing the moving. And this is the idea I had. I called it the warp drive because it gave me a similar idea to what happens in science fiction. But it's this idea of warping space to be able to move fast, very fast. And there's no limit to how fast space can expand or contract. So in principle, you could use this sort of warp bubble to move faster than light. So that was the idea I had in '94. Now there's a price to pay, and nothing is free. So the theory of relativity tells you that curvature or this geometry of space-time can be deformed, but it's deformed through the effect of gravity. So you need large concentrations of mass and energy to produce a deformation of space. And there's some equations, we call them the Einstein field equations, that tell you if you have this concentration of matter, you will produce this deformation of space. And that's the normal way in which we go about it. We think, okay, we have a star, and the star has this concentration of mass, and we go through the equations and figure out what the deformation of space related to the star is, and then that gives us the gravitational field of the star. But in this case, I did it the other way around. I said, I want this very specific deformation of space, this warp bubble, and you go through the equations backwards, and it tells you what sort of energy density, what sort of mass distribution you needed to be able to produce this strange deformation of space. And when you do that, you find that it's something very nasty, because you need something with physicists called negative energy, which maybe doesn't say much to ordinary people. But if people remember this famous equation E equals mc squared, that tells you energy and mass are the same thing, then when we talk about negative energy, we're really talking about negative mass. And negative mass, as far as we understand, does not exist in the universe. So that's a big problem with the warp drive. You need negative energy. And even if you have negative energy, you need huge amounts of negative energy, because to deform the space, it's very difficult to deform space. It doesn't like to be deformed. So in order to deform space a lot, you need huge concentrations of mass. You need planets, entire planets of energy to be able to deform space even a little bit. So you would need for the warp drive the equivalent of a Jupiter-sized object, but on pure energy, and also the energy would have to be negative, not positive. So that's a big problem with the warp drive. But the idea was just this basic idea that you can actually deform space, and it would allow you to travel faster than light if you deform it in the right way.
The idea of the warp bubble and warp drive, what inspired you to think about this? Was it science fiction, as in Star Trek?
Yeah, I was actually watching an episode of Star Trek, The Next Generation. I don't remember which episode it was, but it was some episode of Star Trek, The Next Generation. Sometime in '92, I was doing my PhD at the time in Britain. And watching this episode, they keep always talking about the warp drive and the warp drive. And I was doing a PhD in black holes at the time, in black hole collisions precisely, and I was using Einstein's theory of relativity all the time. So I started thinking, how maybe if they talk about the warp drive, they mean that you're deforming space. So how could you really deform space to be able to do something similar to what they do in science fiction? And I started thinking about that, and then I had this idea of the expansion and contraction of space, the expansion behind you, the contraction in front, this sort of bubble. And then I went back to the office and I did some quick calculations to see if the idea could be expressed mathematically in a simple way. And I found that yes, you could express it mathematically in a relatively simple way. So I did it, and then eventually I published a paper about that. I was doing my PhD at the time, so I was still a student. I went to my supervisor to tell him about the idea, and I had already written something up. And I was afraid he would tell me to just stop thinking idiotic ideas and go back to work. But he was actually very supportive. He told me that it was a very nice idea, and he helped me publish it. So it was actually my first scientific paper.
And on that note, we have to go to break. Be sure to like, subscribe, and hit the bell for this channel if you like interviews like this. And we will be back in a moment, and we'll talk much more extensively about the idea of a warp bubble.
If you'd like to support Event Horizon, you'll be pleased to know we've recently launched a Patreon. Link in the description below. Or alternatively, you can use your cellular telephone to scan the assemblage of squares on screen now. Be sure to like, subscribe, and share the video. And now, back to John.
And we're back with Dr. Miguel Alcubierre. Doctor, you were inspired by Star Trek which is something that I think is important, because science fiction tends to inspire the imagination for anybody from scientists down to the common person. You were inspired into thinking about, could you create a warp field? Now,
exactly. Yeah.
Tell us more about this warp field where you could create a geometry, I suppose, of space-time, where you have one area of space-time in front of the ship, and the ship is stationary within a piece of space-time, essentially broken off from the rest of space-time. So how does it work? Is it less dense in front of the ship and more dense behind the ship? How does this work?
Well, it's not so much density. It's a dynamic thing. Space can contract and it can expand. So in front of the ship, you would have a region in which space is contracting very violently and very quickly. And behind it, you would have an opposite region in which it's expanding very violently and very quickly. And it would do this in a thin shell. So the idea is that you would have a sort of relatively large region of space in which space is quiet and nothing is happening to it. And you're sitting inside this region. And then on the boundary of this region, you have a very thin shell in which there's either expansion behind you or contraction in front of you. And this is a very violent effect, so it can move you very fast. So that's the basic idea. And this is, when we think about a field here, we're talking about really what's really the gravitational field. The gravitational field is the geometry of space-time. That's how we understand it. So it's the gravitational field, the one that's producing these. Now, you can think about another kind of field or energy field or something that's the one that's producing this, right? So because if you want to deform space, you need some concentration of energy or mass. So the easiest thing is to think that it's not so much mass that you're carrying around with you, or negative mass, is some sort of energy field that you're projecting. And this energy field has a very large negative energy, and this produces this strange curvature, a strange expansion and contraction of space in front and behind you. So that's the basic idea. I never went very much or very far into the details. I just wanted to show that this was in principle possible, that the equations of general relativity allowed for the formation of space that looked like this. And I also showed very quickly that you would need this negative energy, which is a big drawback, because as far as we understand, we don't have it in the universe. So that's basically how I left it. And then I never worked back on that again. So a lot of people have worked on that in the past 25 years, but I never went back. I only wrote the first paper, and then I've been just looking about what people say about it.
You introduced an idea and saw what happened.
Exactly.
So because of mass energy equivalence, if you see and you have evidence of negative energy, which maybe there is a little bit of evidence for that. There's certainly nothing for negative mass. But is there any evidence that we could create such a material?
Negative energy might be possible in small regions of space and in very small quantities. I'm not sure if that would be useful for the warp drive, because one thing is maybe it's possible, but maybe you can't control it very well, and maybe it's a very small quantity and you need huge amounts of it. But still, it's possible that negative energy exists. We have hints about it. Quantum theory tells us that in some circumstances, something that like negative energy happens. For example, a very classic example that comes from about 50 years ago is something that comes from quantum mechanics, quantum field theory, and it's actually called the Casimir effect. And the Casimir effect, the idea is you put two parallel metallic plates very close to each other, and the metallic plates conduct electricity, and that means that even if they're not charged, they produce some sort of boundary conditions for the electric field, and it's because they're conductive. So inside, between the plates, then you can only have a very definite number of modes of the electric field, those that fit in there. It's like a string. If you have a string in a guitar, it can only oscillate in a given certain ways because of the length of the string. So this is the same idea, that the separation of the plates makes the electric field in the middle, allows it only to oscillate in very specific ways. And outside of those plates, the electric field can oscillate any way it wants because there's no restriction. And we know that according to quantum theory, the vacuum is not empty. So that means that the vacuum is actually full of fields popping in and out of existence all the time. We call that the vacuum energy, or the quantum vacuum, or the vacuum energy. And since outside you have more freedom than inside the plates, that means that inside the plates you have less vacuum energy than outside. And if you define the vacuum energy outside as zero, then it means that inside the plates you have negative energy because it's less than zero. So that's an effect that we've known for about 50 years. It's a completely theoretical idea. It hasn't been measured, not the energy. There's a secondary effect that all these things would imply that the plates feel a small amount of force, and there will be a force that will try to put them together, to bring them together. This is called the Casimir force. And I understand that the Casimir force has been measured. It's a very difficult experiment, but apparently the Casimir force has been measured. But this negative energy inside has not been measured. Now, if it does exist, and it probably does, it would be a very small amount of negative energy. So it's not enough for a warp drive by far. And even then, it's not clear how you can manipulate that. So it's very little and not very easy to manipulate, so I'm not sure that would help. But there's this hint that maybe in some cases negative energy exists. Then we also know a separate case in which is not so much negative energy, but there's something like anti-gravity going on around in the universe. And maybe anti-gravity could also be used for the warp drive. It's not clear at the moment, but maybe we could. And when I talk about anti-gravity, we normally think of gravity as a force that brings things together, that planets attract each other and objects attract each other because of gravity. Anti-gravity would be a repulsive form of gravity that would make things repel each other. And this might exist because we've seen in the universe at large for the last just over 20 years, we've realized that the expansion of the universe is accelerating instead of decelerating. It's going faster and faster all the time. And the only way in which we can understand this is by postulating some sort of anti-gravity in the universe at large. We normally call it dark energy. So if you hear about dark energy when people talk about the universe, is this mysterious form of energy, an energy field that produces a little bit of anti-gravity that causes the expansion of the universe to accelerate. And this anti-gravity might be useful for the warp drive. I'm not sure. I've tried to do some calculations in the past, but I've never been able to go very far. But my hope is that, yes, maybe dark energy could be used to do something similar to a warp drive at some point in the future, but still not clear at this point.
So because of mass energy equivalence, Einstein's famous equation E=mc², if you can find some sort of negative energy, whether it's dark energy or Casimir effect or what have you, does that suggest that you could create and actually perhaps manufacture negative mass, an object that has negative mass?
Yeah, it's a good point. And one what might think that is possible. I don't think it's very likely because when we think about mass as such, we're actually thinking on particles, elementary particles. We have no hints that there's any elementary particle with negative mass. In this case, when we think about negative energy, it would be more like an energy field, and the energy would not so much be negative per se, but just less than the vacuum. And the vacuum, if we define the vacuum as zero, then it would be negative, but it would be more like that, like less than the vacuum. And it's difficult to see how you can translate that into a particle and make a particle with negative mass. So even though it might be suggested by the formula E equals mc squared, I think in practice there's probably not that easy or not true at all, that you could create a particle with negative mass. But it's true that nothing forbids it. In the physical laws, we know there's nothing that forbids to have a negative mass particle. It's just it would do very strange things, and we have never seen something like that.
In other words, the universe does not ban the existence of something with negative mass. Say you have an apple made of negative mass, that would be anti-gravity. The universe doesn't forbid it, but that doesn't mean it can exist, right?
So, yeah, it's not so much the universe doesn't forbid it. It's the laws of physics as we understand them today don't forbid it. It might be very well that the universe does forbid them, but we just don't know how, right? So it's the laws we understand does not forbid it, but there's no indication that that's something that can happen, right? It's not the same. So there's things that are not forbidden by the laws of nature but don't happen. For example, the laws of nature are the laws of mechanics, Newtonian mechanics, are reversible. So in principle, if it can break a glass in the floor, the laws of mechanics would allow the process to be reversed, to all the pieces of glass to jump together and coalesce into a full-formed glass and jump into my hand. That's allowed by the laws of physics, but it doesn't happen, right? Because it violates all the things like thermodynamics and things like that. So It's just statistically not likely to happen. So it might be something like that the laws of physics do not forbid negative mass, but maybe it's, again, statistically unlikely in the same way as a glass reconstructing itself would be unlikely, right? So very, very unlikely, right?
Say, let's conjecture for a moment. Say that it could exist. Is there a way for the Big Bang to have produced matter with negative mass?
If they do exist, then they should have been produced in the Big Bang. The Big Bang, there was so much energy around that essentially any particle that could exist was created. Most of those particles don't live very long. So that would be another question, right? You have a negative mass particle, how long does it live? So most elementary particles we know about are actually unstable, and they decay very quickly into other types of particles. And in the end, we're only left with a few stable particles, which the ones we were taught about in high school, right? The proton, the neutron, and the electron. And everything is made of those three because those are the only three that are actually survived because they're stable. All the other zoo of particles that we know from particle physics are unstable. But they're all produced at the Big Bang, because at the Big Bang there was so much energy available that everything that could be produced was produced. So yes, if negative energy particles can exist, then in principle they could have been produced in the Big Bang. But the next question would be, how long do they live? If they don't live very long, we wouldn't see them around. And it would be interesting if there was some sort of stable negative energy particle, but then we would have seen it. That's what we would expect, right? If there's some sort of stable particle, then we should see it today, because since it's stable, it should be around and we should be able to detect it, right? And we haven't been able to detect anything like that. So if they do exist, they're probably not stable.
Now that's somewhat of a mystery in and of itself within physics, is if the Big Bang created antimatter, then shouldn't we see what happened to all the antimatter? It should have been an almost equivalent amount to normal matter, but yet we don't see it, leading to questions about did most of the universe annihilate, as far as matter goes, early on in the universe?
Exactly. That's an excellent question. It's one of the biggest puzzles and mysteries of modern physics that we don't know the answer to, and we're certainly worried about that. So yes, in the Big Bang, as far as we understand physics today, an equal amount of particles and antiparticles should have been produced, and then those particles should have annihilated each other when they found each other. When a particle and an antiparticle meet, they annihilate each other and they produce pure energy. So we should live in a universe of pure energy, because all the particles and antiparticles should have annihilated each other and should have been exactly equal amounts of them because of the symmetry. And of course, that's not the case. fortunately we're around and there's matter around. So for some reason, there must have been at the beginning a slightly larger amount of matter than antimatter. Maybe a very small fraction, but a little bit more matter than antimatter. And when the annihilation occurred, some matter was left behind. We don't really know why. That's a big question. People have been thinking about that for 50 years at least. Famous physicists and even Soviet physicists like Gamow and things like were thinking about why matter prevails over antimatter. And people are still thinking about that today, but we don't have a clear answer yet. But it is one of the big mysteries of modern theoretical physics. Why there's matter and no antimatter around?
Back to matter with negative mass. How would this stuff behave? It would be, by its nature, anti-gravity. So if you were looking for it in nature, would it immediately eject itself out of a galaxy, or would it concentrate at certain points in a galaxy where you have this gravitational equilibrium going, or would it be out in the intergalactic space?
It would produce a different type of gravity. So a large object made of negative mass would produce a gravitational field that would be repulsive. So instead of falling into imagine you have a star like the sun, but it's made of negative mass. So instead of falling into it, you would be repelled by it. You would fly away from it, because the field it produces is opposite. So it would produce a repulsive field. Now, as far as small particles, that's not true, because a small particle, it doesn't matter. That's one of the things we know about gravity, that the trajectory of a small particle when it's moving in a gravitational field of a much larger object, the trajectory it follows is independent of its mass. So it doesn't matter if the mass is positive or negative, it would do the same thing. So if we have the sun, and the sun is normal, a normal star of positive matter, and we had an Earth made of negative mass, it would still go around the sun exactly the same way the Earth goes around the sun. Because the mass is much smaller, and it doesn't matter if it's negative or positive, it would follow the gravitational field of the sun, and that's attractive. So it's more like that. Large amounts of negative mass would produce a repulsive gravitational field, but a negative mass particle would not be repelled by the sun. It would still be attracted by the sun, because it doesn't matter which side the mass is. So yeah, small particles of negative mass would not be expelled from the galaxy. But if they clump together into a larger object, that object would be repulsive. Things would fly away from that object.
Now, with this concept of negative matter, I suppose you could call it, this is also important with things like creating stable wormholes and essentially any speculative way we could conquer the speed of light, so to speak. Yeah. Now, the universe doesn't ban it, but we have no indication of it. How could we detect such matter, which I guess would be the first step in trying to harness its power? How could we detect this negative mass material if it existed?
At a distance, it would be difficult. You would have to find some sort of object, very large object in space that instead of attracting nearby objects, repels them. But if there was a galaxy with negative mass, then we would have seen it, because we would see that the trajectories of other galaxies close to it are repulsive instead of attractive. So maybe we should be able to see it in large clusters of galaxies if there was a galaxy there with negative mass. If the object is much smaller, then it's very difficult to detect. If you have individual particles with negative mass, then we should see those in particle accelerators. And then we should be able to measure it, because essentially energy is conserved. So in an interaction with particles with negative mass, you would see that you gain more energy than you put in, because some of the energy became negative and you ended up with negative energy particles. So that you should be able to measure that in the energy balance in particle collisions in an accelerator. So that we would have seen in an accelerator, and we haven't seen it. But as far as much larger objects in the universe, those are difficult to detect unless they're extremely large and have a big effect on the surrounding space-time. But I think it would be difficult to see. But again, there's no indication that they exist, because if there was negative energy particles, we would see those on a laboratory on the accelerators, and we haven't.
So no evidence whatsoever.
No, unfortunately.
Now, back to the warp field. If you were in a spacecraft sitting static within the warp field, and you were traveling across the universe at superluminal speeds, what would that be like? Would you experience radiation? What would being inside the warp bubble be like?
Yeah, there's some people that have thought about that, and they've even done some simulations as to how the stars would look like if you're sitting inside a warp bubble. So essentially, if you're going very fast, even faster than the speed of light, the first thing you would notice that the stars in front of you, first you would see them in a very small cone in front of you. So you would see stars only in a very small circular region directly in front of you. Everything outside that small cone you wouldn't see because the light wouldn't be able to reach you because you're going faster than the light. So you wouldn't be able to see anything behind you because nothing would be able to catch up with you, not even light. So behind you it would be totally black, but also in front of you in a large region, only you would see only a small circle of stars. But again, if you're going faster than light, then any light that hits you from in front is going to be blue shifted. So it's going to increase in energy. We call that a blue shift. It's similar to what happens with an ambulance. When it's coming towards you, you hear a very high pitch. And when it's moving away from you, you hear in a very low pitch. So it's the same thing with light.
Doppler effect.
It's Doppler effect.
Yeah.
So you would see the light coming towards you blue shifted. So again, it would be far more dangerous because something that's normally just ordinary light will probably be hitting you like gamma rays, and those are very dangerous. And so you would receive a lot of radiation from the front of the ship. And also anything else that is in your path. If there's a rock in your path or something like that, you would hit it at a huge speed and it would probably be deadly, even a small grain of sand. Right? So yeah, it would be extremely dangerous unless you had a very high efficiency shield to shield you from the radiation coming from in front and also from any small speck of dust that could hit you and destroy the ship. So everything that hits you comes with higher energy because it's shifted, right? So yeah, that's essentially what you would see. So whatever light comes in front of you would be shifted even probably towards gamma rays, depending how fast you're moving. It would be deadly, and you would need a big shield. But then you would see also this deformation. Only a small region in front of you would be able to reach you. Everything else won't be able to catch you. And as I said, I haven't done these calculations myself, but people have done them, and they've done simulations over the years about how it would look like from inside the warp bubble. And this is sort of the things you find.
So if you were traveling through space at at faster than light speeds, we're not even talking about relativistic speeds, we're faster than that, and you caught up material in front of your ship, if you came out of warp in front of a planet, you could do some serious damage to that planet by that material, right?
That's a very good observation, and it's also something people have actually done calculations on. Anything that's in your path and doesn't directly hit you, if it was moving forward, say, but not as fast as you would catch it, but then it would be sort of stuck in the front of the bubble. It wouldn't come inside the bubble because it was moving towards forward, so it wouldn't actually hit you, but it would be stuck in the front of the bubble. So the front of the bubble forms like a barrier that is sweeping particles and energy in front of you. And you would be accumulating a lot of energy. So any light, for example, that you catch, because you're moving faster than light. So if you catch light that was moving forward, but not as fast as you, because you're moving faster than light, it would get stuck in the front of the bubble. And then you will catch a lot of light in that way. And when you stop, all that light that you caught would suddenly just go forward to whatever's in front of you. So yes, it would be extremely dangerous when anyone in front of you, it would be extremely dangerous even if you don't stop it, because then you would hit them, right? But even if you stop, then all the radiation would be released and it would burn anything in front of you. So yeah, it's dangerous.
So, and there comes the question of, how do you slow down once you accelerate? And we'll get to that in a minute. We have to go to break, but never point your warp drive directly towards your planet destination.
Exactly.
We'll be back in a moment with Dr. Alcubierre.
The following program contains imagery from Mark Rademacher, designer of futuristic hardware and founder of Holland Space Yards.
What? Tell him thanks.
Yes, John, I'm doing it now. Thanks, Mark. Thanks.
Tell him thanks. And we are back with Dr. Miguel Alcubierre. Now, Doctor, the big problem with traveling at these speeds is that you can also bring in time as a problem, because whenever you go faster than light, you always have to ask the question, what does time travel have to do with this? Tell us about that. What effect here do we have on time?
Yeah, well, there's separate issues here. So one thing that people might have heard is about the time dilation. When you're traveling very fast, but still lower than light, but close to the speed of light, then time moves forward very slowly for you as compared to things that are not moving, right? So if you go far away from the Earth, very close to the speed of light, and then come back, say to a distant star a few years away and then come back, then you might find that for you it was only a few years, and maybe on Earth it was 100 or 1,000 years or even more. Depends how fast you were going and how far you were going. This is time dilation, and it happens also if you travel slower than light. Now, in the model I did for the warp drive, I on purpose put out this effect. So the warp bubble that I designed doesn't have any time dilation, but that's by construction. And since the construction is a little bit just like I wanted to make it, and I did it simple, it doesn't mean that if you could do it in real life, it would be like that. But in the model I have, there's no time dilation, so you wouldn't have this effect. But the other effect that you also have when you travel faster than light is worse. You can show, and this is something that Einstein showed very early from his special theory on relativity, that if you can travel faster than light, in principle, you can build a time machine. Because if you travel faster than light, then from the point of view of some observers, you're actually traveling back in time. So if you do it there and backwards, you could end up coming back before you actually left. It's not easy, it's a special construction, but you can do it in principle. So, and there's a proof, a general proof, that any method you come up with that allows you to travel faster than light can in principle be turned into a time machine. That's true of the warp drive. I didn't prove it myself, but I hinted at it in my paper, and somebody proved it about a year later. Somebody actually proved it in detail. So you could use a warp drive to build a time machine, but you can do the same with wormholes. So people talk about wormholes to travel faster than light. If you can build a wormhole, then in principle you can also turn it into a time machine. So in a way, you could step into the wormhole today and come out of the wormhole yesterday, which again is weird. But it's true. As far as we understand, any way you come up with to travel faster than light allows you to, in principle, build a time machine. Now, physicists as myself, we don't like time machines, because time machines mean you cannot predict the future, because anything you were going to predict can be destroyed by somebody coming from the future and changing it, right? So in principle, it means that physics would not be predictable. We wouldn't be able to predict what happens in the future if time travel is allowed. And it brings with it a host of paradoxes, like the famous grandfather paradox and all those crazy logical paradoxes. So we don't like it. We don't like time travel to the past. And so Stephen Hawking in the early 90s and late 80s, I think, he came up with an idea that he called, in very technical terms, the chronology protection conjecture. But in layman terms, it actually means the no time travel idea, if you want. So he argued that the laws of physics do not allow time travel to the past, and if you were able to try to produce a time machine, something would happen that would prevent you from doing it. Maybe the time machine would blow up in your face, or maybe a black hole would form. And we came up with this idea. It's not just a general argument in words. He actually came up with some mathematical calculations based on quantum theory, and he showed essentially that if you were able to produce a time machine to travel to the past, and a feedback loop would occur. It's similar to what happens when you have a microphone and a speaker close by, right? So you hear the feedback because sound is going around and around, and it's getting stronger and stronger because of the amplifier. And everybody has heard that when you're talking in a microphone and you get too close to the speaker. So it's the same idea, but Hawking argues that it would happen in a time machine. Energy would be trapped in a loop in time and going round and round and round. It would be amplified. It would be focused and amplified with each loop, and eventually this would create such a huge concentration of energy that either the machine would blow up or a black hole would be produced, and that would happen essentially instantaneously because it's a time machine, right? So from your point of view, it would be instantaneous. You would switch on the time machine and it would blow up or produce a black hole, and you would not be able to use it. So that's essentially Hawking's argument, and it's been around for 25 years. It's still just a conjecture because there's no formal proof that this happens. It's just an idea, but it's a good idea based on very solid mathematical foundations, but it's not a formal proof. So that for me is good, right? Because that means that it doesn't mean that you cannot travel faster than light. It means that if you want to turn your faster than light spaceship into a time machine, you wouldn't be able to do so. And I think that's good. That means you would, in principle, might still be able to produce a warp drive and still not have a time machine. And at the moment you would try to use it to build a time machine, you would die in an explosion or something. So for physicists, I think it's a good idea. And even for the warp drive, it's probably good news. It means that one of the arguments against it, that is you could turn it into a time machine, wouldn't be true, right? You wouldn't be able to turn it into a time machine. So that's essentially the situation there.
In short, it would be isolated in that since you've isolated a piece of space-time and you're not moving within it, then you are not actually manipulating time.
Well, yeah, exactly. If you just go on a one-way trip, then that's true. The thing comes around if you try to do a return trip, and if you do it in a very special way, in principle, you should be able to do a time machine. But this Hawking's argument tells you that you wouldn't be able to.
So the laws of physics protect us from time paradoxes in this case.
That's essentially Hawking's conjecture. The laws of physics protects us from time travel. Time travel to the past. Time travel to the future is always possible.
Sure.
You just can't come back, right?
We're always constantly traveling into the future. We just can't go to the past.
Exactly.
Now, how does this relate to Einstein and things like closed time-like curves? Because some people say that maybe backwards time travel might be possible through that mechanism.
It's exactly that. It's exactly that. So when physicists talk about time travel, we always mean in technical terms closed time-like curves. So time travel from the point of view of physics is the fact that you have a trajectory that you can follow that brings you back around in a circle. And a trajectory that you can follow is always a time-like trajectory because you can follow it in your own time. So it's a trajectory that a particle like us can follow. It's called a time-like trajectory. And if you can bend on itself and turn around back, then it's called a closed time-like trajectory. So any type of time travel in physics today is always understood as a closed time-like loop. And what Hawking is telling you that closed time-like loops cannot exist in nature because something catastrophic would happen as soon as you want to produce one. But every sort of idea of time travel, even Gödel, who had an idea of a strange universe in which time travel could exist, is called Gödel's universe, and it's from the 20s of the 20th century. That also has closed time-like loops. So in principle, you construct geometries. You can construct geometries with these loops that allow time travel, and you can construct them easily. Mathematically, it's not that difficult to come up with examples. But what Hawking tells us is that in practice, you wouldn't be able to do this because these sort of spacetimes would be unstable against quantum perturbations. That's essentially Hawking's argument. If you forget about quantum mechanics and you just do a purely classical general relativity calculation, in principle, you can always make them. It's not even difficult to come up with little models. But in practice, if you try, quantum mechanics would intervene and it would be unstable, right?
Which is a big problem with everything. You know, when you start talking about stuff like this, is instability, like a wormhole would, yes, there's a wormhole at the singularity of a black hole, but it's going to open and close rapidly, and you're not going to be able to traverse it. So, and this is where the negative matter comes into play, because you would need that in order to stabilize the whole thing.
Keep it stable. Yeah, a wormhole on its own, it's unstable. And that even has nothing to do with quantum mechanics. That's just pure relativity. In pure relativity, a wormhole in empty space or with positive mass, it's unstable. If you want to stabilize it, you need negative energy because the wormhole wants to close. The equation tells you that whenever you open a wormhole, it wants to close very quickly. And you want to keep it open, you need a repulsive field, and that's negative energy that keeps it open. So that's the reason why you need negative energy in wormholes. But it turns out anytime you want to do something crazy with Einstein equations of relativity, anytime you want to produce some crazy geometry like a wormhole or a warp drive or something like that, apparently always you need negative energy. It sort of comes out always, right?
Anytime you want to circumvent the laws of the universe, it says you're going to need something special in order to do this. And back to the warp drive. If you were able, just to speculate, to create the warp field and travel at many times the speed, relativistic speeds, is there a speed limit? Is there some barrier that says you can't go faster than this with the warp field?
There's no speed limit in principle. It's just to go faster, you would need more and more negative energy. And the more negative energy you have, the faster you in principle could go. You could also use a warp drive to move slower than light. It would be a very inefficient way to do it, but you could use a warp drive to move slower than light. And faster than light is as fast as you want to go, depending on how much negative energy you have available. So there's no limit. But there is a problem that I haven't actually mentioned yet. It's the second problem with the warp drive. We call it the horizon problem. And it has to do with when you use the warp drive to move faster than light, then in front of this bubble of the formed space at the front region, there's a limit further to which you cannot actually access anything in front of that directly from inside the bubble. So if you're inside the bubble, you can only reach so far in front of the bubble, but not all the way in front of the bubble. So there's a horizon that forms there. So there's a region you cannot reach. And this is a problem because if you're supposed to be putting the negative energy in place from inside the bubble, say you're in a spaceship and you have some sort of energy field generator or something like Star Trek, and you use this generator to put negative energy at the front of the bubble to be able to move, then there's a region you can't reach. And that means you cannot put enough negative energy there, and you wouldn't be able to produce the bubble in the first place. So this is the horizon problem. It doesn't. If you want to use the warp bubble to travel slower than light, then there's no problem. But if you want to travel faster than light, then it's a big problem. And that means that the spaceship itself would not be able to produce the required field. It would have to be produced from the outside. And that, again, it's a big problem, right? Because somebody would have to be there producing the negative energy as you go along, as you pass. So you could imagine maybe a sort of big tube, like a subway tube, right? A big tube through space with field generators that are switching on in time as the spaceship is going through. But that seems like completely crazy, right? To build a tube from here to Alpha Centauri.
So essentially, you need to build a highway before you could use the drive. So you would have to have
you need to build a highway before you send anything through it. Yeah.
So how would you do that? If you would have to do it at sublight speeds. You'd have to have a spacecraft, and you would have to leave some sort of negative mass generators of some sort in front. So to build a highway to have it, it's sort of like gas stations, actually, where
exactly. You need to send a spaceship before, slower than light, that would be leaving behind it negative energy generators along the way, and this would give you this sort of highway. And once it's built, something can go through it faster than light, but it would have to be built before, and that would have to be done slower than light. Yeah.
Now, once you had this highway built and you could traverse, well, at sublight speeds, obviously, it's very difficult to traverse the universe, but the galaxy, say, you were able to build a highway over millions of years and create this sort of transit system. What, with a warp bubble, could you detect that? If say an alien civilization millions of years ago created such a thing, and you were looking for alien technosignatures, what would that look like? This Alcubierre warp drive highway system. I mean, could you detect it, or would it just be not visible?
I think I have never thought about this in detail, but I think if it was moving directly towards you, you should be able to see a burst of radiation when they're using it. But if it's not moving directly towards you, then I don't think it would be detectable. I don't think you would be able to see anything. But if it's pointing directly at you, then yes, you would see a burst of radiation, especially when they slow down, as we mentioned. But yeah, you should see. But I think it would be difficult because something very localized, and it's not really pointing at you, then I don't see what you would see. So it's probably undetectable.
You mentioned slowing down. Once you get going, how do you slow back down with this concept?
That's exactly what I was saying. It's the same problem with the horizon. So you wouldn't be able to slow down on your own. Somebody would have to do it from the outside. So somebody would have to switch off the highway as you arrive at your destination. You wouldn't be able to switch it off from inside. It's for the same reason, because you cannot reach the front of the bubble, so you cannot tell it to switch off, at the front at least. And it's exactly the same problem. So initially, when I did this paper, I mentioned this also in passing. I mentioned that they wouldn't be able to slow down once you turn it on. But then I realized the problem was actually much worse. You wouldn't be able to turn it on in the first place, right? So that's because of this horizon problem. But it's basically the same problem. If you're traveling faster than light, you cannot reach the front of the bubble, which means you can't manipulate it. You cannot not turn it on. You cannot turn it off. You can't manipulate it at all. Somebody has to do it from the outside that was already there waiting, right?
So essentially, you cannot ever reach the brake pedal.
Basically, yes. It's a good analogy, but yeah, it's essentially as if the brake pedal was so far away you wouldn't be able to reach it yet.
Yes, you can't ever reach it physically. Now, inside the warp bubble, you would also probably have problems. People have said that you would be cooked by radiation. Can you get into that?
Yeah, well, that's what I was mentioning. Anything coming towards you from the front, as you reach it with a warp double, any radiation that was pointing towards you would actually be blue shifted. And if you're moving much faster than light, it would be blue shifted a lot. So even something that was ordinary radio waves that was completely harmless, if you're traveling sufficiently faster than light with the warp bubble, it could be blue shifted towards gamma rays and kill you, right? Because the radiation would be so intense. So you would need a very good shield if you're planning to use this with traveling faster than light. But this is a problem even if you move slower than light. If you build a spaceship that could go, say, 99% of the speed of light, then again, that's a danger. Because radiation that's coming towards you, ordinary light, it's blue shifted, and it's blue shifted towards gamma rays, it would be deadly. And if you find a small rock and it's hitting you at 99% the speed of light, then it could destroy the ship. So this is a problem even at slower than light speeds if they're sufficiently high, right? At 99% the speed of light, this is already a big problem. So it's not a problem that's just related to the warp drive. It's a problem of moving at very high speeds.
On a scale of 1 to 10, with 10 being the most unlikely, where would you rate the possibility of the warp bubble that we could actually, at some point in the far future, create this? How likely is it?
Okay, yeah. So 10 is the most unlikely?
Yes.
So I would probably put it at a 9.
At a 9?
I think it's very unlikely. If you ask me, even though it's my own idea and I like it for personal reasons, I think at this moment it might seem even more likely to have wormholes, and those would have fewer problems. Still, wormholes are not likely at all because we have no idea how to build one, but they have fewer problems. If you could build a wormhole, then you wouldn't have this horizon problem, you wouldn't have this radiation problem. A lot of the problems with the warp drive are simply not there in the case of wormhole. But again, nobody knows how to make a hole in space, so we have no idea at all how to create a wormhole, but it seems less problematic if you could actually have one. But yeah, I think it's, unfortunately for myself, because it's my own idea, but I think it's highly unlikely at this point.
Still an interesting idea, and it's always fruitful to entertain useful ideas, because that's where maybe other useful ideas come from.
Yeah, I agree completely, yeah.
And on that, we are out of time. Dr. Alcubierre, thank you for joining us.
It's been a pleasure, thank you.
Thinking about far future technologies is a very uncertain thing, vexing at times given what I do. Imagining something is one thing, and actually engineering it and building it is entirely another. But imagination is important. That's what starts the ball rolling and gets people thinking about the nuts and bolts of an idea. And while the materials and technology needed to create an Alcubierre warp field lie in the future, perhaps even the distant future for all we know, it is at least a seed for thought on the subject right now. That's important. And who knows, there may be other ways to defeat the speed of light. There are always the possibilities of wormholes, or even ways we may not have thought of yet. We do not yet have a complete understanding of our universe, only a partial one. So the concepts that spawn out of science and sci-fi in the coming years, centuries, or millennia may serve as seeds to push us further. Who knows where we might end up?
John!
Yes?
I think it's time to talk about getting rid of the car.
But wait, well, I have an idea.
Oh dear, this isn't a good sign.
If, and I stress if we can get Alcubierre to drive the LeBaron, we can increase its value tenfold.
Oh no, I can see where this is going.
Wait, stop! How did you even use a spray bottle? We'll figure that out later, and joining me next week will be Dr. Duncan Forgan for a discussion of the Fermi paradox and the solutions to it.